Hello, this is the Mathematic Fanatic, and you are watching Approximating Square and Cube Roots. So I wanted to make this video. I thought of the topic yesterday after looking through my old schoolwork, and then when I wake up today, I see that Michael Penn created a video on the exact same topic. So I will link to his video in the description, but I plan to expand on his video. He showed that x sub n plus 1 equals 1/2 all times x sub n plus s over x sub n converges to the square root of s for initial values of x between 1 and square root of s non-inclusive. He used calculus to show that it converges. However, I will show that it converges with an initial guess of x naught is greater than the square root of s, which is greater than 1, without using calculus, since using calculus is kind of unneeded. So the proof. To show that the limit as n approaches infinity of x sub n equals the square root of s, we will show that x sub n is greater than x sub n plus 1, which is greater than the square root of s. So since we're given that x naught is greater than the square root of s, then our base case holds. Then assume inductively that x sub n is greater than the square root of s. First show that x sub n is greater than x sub n plus 1. We can take the given formula, x sub n plus 1 equals 1/2 all times x sub n plus s over x sub n, then subtracting x sub n from both sides. We get the difference between the consecutive terms, then the original recursive step minus x sub n. However, since we have a 1/2 x sub n here and a negative x sub n here, that just turns out to negative 1/2 x sub n, right? So you can reverse distribute to get it back, which then you can use a common denominator of x sub n to get s minus x sub n squared all over 2 times x sub n. And we know that is less than 0, in other words, negative, because we assumed that x sub n is greater than the square root of s. So s minus x sub n squared is going to be less than 1. And we know that x sub n is greater than 1, so it has to be positive. So that's how we get the negative. So we just proved that x sub n is monotonically decreasing. Now to prove that it is bounded by the square root of s, we square both sides and subtract s to get x sub n plus 1 squared minus s equals the square of our original recursion minus s equals 1/4 times the square of our recursion distributed, all minus s. We have a 1/4 and positive 2s here. Then subtracting s, that would give us the same as subtracting 4 over 4s, right? So 2 over 4s minus 4 over 4s. That just ends up to be negative 2 over 4s, right? So that's where I get that from, which that's also just the same square, but with a negative. It's the square of the conjugate. So we know that a squared number over a constant that is positive is always going to be positive. So that's how we get is greater than 0. Now we have shown that x sub n plus 1 is greater than the square root of s. So now just to compute the limit. So the limit as n approaches infinity of x sub n plus 1 equals x, because it tends towards x, which means the limit as n approaches infinity of our recursion for x sub n plus 1 equals 1/2 x plus s over x. We are then able to multiply both sides by x to get x squared equals x squared over 2 plus s over 2, which then multiplying by 2 and getting all the x terms on one side, we get x squared equals s. And therefore, since all x terms are greater than s, which is greater than 0, the initial condition, we end up getting the limit as n approaches infinity of x sub n plus 1 equals x, which equals the square root of s. So how do we do this with cube roots? So now that we've shown that the square root approximation formula works and it converges to the square root of s, we want to show the similar sequence for the cube root converges. This is the following formula. X sub n plus 1 equals 2 over 3 x sub n plus s over 3 x squared sub n, where we are trying to approximate the cube root of s. I will show that the sequence converges for an initial guess of x naught is greater than the cube root of s, which is greater than 1. I will leave the case where 1 is the lower bound and the cube root of s is the upper bound for x naught as an exercise for the viewer. Hopefully you will be able to use what you learned here today to complete the proof. So to show that the sequence is monotonically decreasing, or in other words, that x sub n plus 1 is less than x sub n, then we can do the same as before. The base case holds that x naught is greater than the cube root of s, then assume inductively that x sub n is greater than the cube root of s. We get x sub n plus 1 minus x sub n, which is the difference between the consecutive terms, equals 2/3 x sub n plus s over 3x squared sub n minus x sub n. So if we have a 2/3 x sub n and a minus 1x sub n, that just equals negative 1/3 x sub n, right? So then we're able to get a like denominator with 3x squared sub n to get s minus x sub n cubed over 3 times x sub n squared, which overall that ends up giving us a negative over a positive, and that's because we assumed that x sub n is greater than the cubed root of s. So x sub n cubed is greater than s, which means that s minus x sub n cubed is less than 0. There we go. Now to show that the sequence is bounded by the cube root of s, or in other words, x sub n plus 1 is greater than the cube root of x. We want to show that the cube of each side of the sequence, then subtract s. So x sub n plus 1 cubed minus s equals our original recursion cubed minus s, which that ends up being this whole thing distributed out. It's very messy, but it's 8/27 x sub n cubed plus 4/9 s plus 2s squared over 9x sub n cubed plus s cubed over 27x sub n to the 6th, all minus s because of the original restraint. So we can actually change this 4/9 s to a negative 5/9 s because we're subtracting 1s. So, and since x sub n is greater than the cube root of s, which is greater than 1, let x sub n cubed equal s plus epsilon for some epsilon greater than 0. This is where the real analysis comes in, because this is a question that I had for my real analysis class when I first took it, and I did not get the question right. So now I'm redoing the question, and I'm trying to get this to work for you, and I was able to. So we get 8/27 x sub n cubed minus 5/9 s plus 2s squared over 9x cubed sub n plus s cubed over 27x sub n to the 6th, which you can all get a common denominator of x sub n to the 6th, and you can plug in for every x sub n cubed, you can plug in s plus epsilon. And we know that this is s sub plus epsilon cubed because when you get the like denominator, this becomes an x sub n to the 9th, this becomes sub n to the 6th, this becomes x sub n to the 3rd, this becomes just s cubed. So that's how we get that. Then, distributing out the s plus epsilons, we get 8s cubed plus 24s squared epsilon plus 24s epsilon squared plus 8 epsilon cubed minus 15s cubed minus 30s squared epsilon minus 15s epsilon squared plus 6s cubed plus 6s squared epsilon plus s cubed. And so notice we have an s cubed here, a 6s cubed here, an 8s cubed here, and negative 15s cubed here. That all ends up being 0 because 8 minus 15 plus 6 plus 1 is 0. Also, with the s squared epsilon, we have 24s squared epsilon here, we have negative 30s squared epsilon here, and we have positive 6s squared epsilon here, which ends up being 0 as well. So we're just left with positive terms because epsilon is greater than 0, s is greater than 0. So all of these are positive. The x sub n is positive, so everything here is positive. So that's how we know that it is greater than 0. Hence, we have shown that x sub n is greater than x sub n plus 1, which is greater than the cube root of s. Now to prove that the sequence converges to the cube root of s, we take the limit. So the limit as n approaches infinity of x sub n plus 1, which equals x, which then equals the limit as n approaches infinity of our original sequence, equals 2/3 x plus s over 3x squared. We can subtract 2/3 x from both sides, then multiply by 3x squared to get x cubed equals s. And since the cube root of s is greater than 1, which means it is greater than 0, so we don't need to think about the negatives, the limit as n approaches infinity of x sub n plus 1 equals x, which equals the cube root of s. Therefore, we have proved that it converges. Now, in conclusion, the square root formula kind of makes sense intuitively, because if you have the value you are trying to find the square root of, and you divide your guess out, the value will either be higher or lower than the square root by some varying amount, which is less for the closer you get, since x squared is the same as x times x. Then taking the average between your guess and the value, which the error ends up lowering the previous guess if it was too high, and increasing the guess if it was too low. I hope that made sense, but put in the comments your solution to the cubic case, where x naught is bounded by 1 and the cube root of s non-inclusive. It's kind of trivial to show when x naught equals the cube root of s, because then it just stays at the same place. Same for the x squared case. Overall, I was planning on making this video anyway, so I decided to do so. I didn't really want to let it stop me that Michael Penn just made the video the same day. However, I know that I've mentioned Michael Penn before, but he is always a step ahead of me. I'm always amazed by him. But I would also like to shout out a few other inspirations of mine, such as 3 Blue 1 Brown, Mathologer, Bry the Math Guy, and so many others. Too many to name. And honestly, I'm probably going to be naming a few of them in the future just because it's where I get my inspiration from. So thank you for watching. I really appreciate it.